Swayam Prabha. Digital India. Educated India.
Welcome to Structural Dynamics class. So in this class we will discuss about three-dimensional structure analysis. So this three-dimensional structure analysis will enable us to analyze the structure in near real conditions. So when we have a structure which is 3 degree of freedom on each floor. So if you take a real structure, what we'll have is say x direction translation, y direction translation and rotation. So these are 3 degrees of freedom which we have in three-dimensional structure. So how to analyze that, how to formulate equation of motion for that, and how to solve. Okay. So those things we will discuss in this class. So first we will discuss about generation of dynamic equilibrium equation, and then how to formulate stiffness matrix, how to formulate mass matrix, and then we will discuss about the eccentricities what are present in between center of mass and center of stiffness. So if you look at this picture, this is a typical single degree of freedom system, actually a single story structure. So a slab which is supported on 4 columns. Okay, so this slab can translate in x direction, it can translate in y direction, it can translate or it can twist, so that means it can rotate also. So if say it is symmetrical, so all the stiffnesses are same in x direction and also in y direction. So what will happen is it will translate. So if I give motion in one direction, it will oscillate in that direction only. So if you look at say this as a slab and then supported by 4 columns. So if I pull in one direction and leave it, it will oscillate. And if I pull in another direction and it will oscillate. And then if I twist it, it will twist. If I give rotation, it will twist. So if I pull and it is oscillating in one direction, so that means what, it is symmetrical along x axis. If I pull in y direction and it is oscillating only in y direction, it is symmetrical along y axis. So how it becomes symmetric along x axis or y axis? So if the stiffness of columns, all supporting columns, is same on this side and on this side, and say center is exactly in the center. So the diagonal intersection of diagonal is center of mass and then center of stiffness. If both lie on the same point, then if I pull, it will translate in one direction only, no rotation takes place. And similarly in the y direction also no rotation takes place. But if the stiffness of say any column is different from the other columns, then even if I pull in one direction, it starts twisting. So this will illustrate more, means I will show you a model and illustrate this in little more detail in the next class. Now let us look at this slab. If I give unit displacement or displacement along x direction, it will translate in x direction. So symmetric about x axis and also about y axis. Center of mass and center of stiffness lie at the same point. So we will discuss about how to calculate the center of mass and center of stiffness. And then if they lie at the same point, that means there is no eccentricity. When there is no eccentricity, there is no torsion in the building. So we can develop equation of motion for this one in a very easy manner. Next, so this is mass moment of inertia. So if the slab is moving in one direction, then how much mass is contributing to its motion? To entire mass vibrating in one direction. So that means what, inertia force will consider the total mass. If it is translating in y direction, entire mass is contributing. But if it is rotating, so that means what, all the points are not at the same distance. So here when I am translating in x direction, all the points are moving with the same amount of displacement. But when I translate, all the points are not moving with the same amount of displacement, but they are moving with the same amount of angular rotation. So that's why we consider mass moment of inertia for that. So mass moment of inertia can be calculated as m into a square plus b square. So a and b are the sides of the slab. a square plus b square by 12. So this will come from the first basic principles of mechanics. Then next one is case 2 where there is no symmetry. So that means what? So purposely we have removed one column. If you can notice here, one column is removed. So in this case, even if I translate in one direction, it will rotate and as well as translate in another direction also. So x direction motion will translate in x direction as well as y direction and rotation. So that's what happens. So unsymmetrical about x axis as well as y axis. Center of mass and center of stiffness does not lie at the same point, and eccentricity is present in the structure, and then torsion will take place. So now what is center of mass and center of stiffness? Center of mass is usually in uniformly distributed load. So this is intersection of diagonals will give us center of mass. And now because only 3 columns are present, so what will happen is center of stiffness will be somewhere here. This is center of stiffness. So this is center of mass. So the distance between this, okay, this is eccentricity x and this distance is eccentricity y. So because of this, torsion takes place in the structure. Now let us develop equation of motion. First we need to find out how to develop stiffness matrix. Okay. So this A, B, C, D, let us assume these are frames. Okay. So and each frame will act along its own plane, but in the plane perpendicular to it, its stiffness is treated as 0. So let Ka, Kb, Kc and Kd are lateral stiffnesses of frame A, B, C and D respectively in their own plane, and then out of plane stiffness of all the frames is assumed 0. So that means what? This frame will offer resistance only along this direction. This frame will offer only along this direction. So that means what? If my displacement is along y direction, then Ka and Kc will give resistance, Kb and Kd's resistance is 0. And if my displacement is in x direction, then Kb and Kd will offer resistance, Ka and Kc are 0. And if I rotate, all 4 frames offer stiffness or resistance. Let's formulate stiffness matrix. So how do we formulate stiffness matrix? We have say 3 degrees of freedom here. So to the center of mass we are writing 3 degrees of freedom. So first degree of freedom is ux, displacement along that, and second degree of freedom is uy, and third degree of freedom is say u theta. So if we give displacement, that is ux as 1, uy as 0 and u theta as 0. So if we give 1 unit displacement along x direction, then what happens is the resistance comes from frame B and frame D. So stiffness of frame B is Kb, stiffness of frame D is Kd. How do we get this frame stiffness? So depending on say number of columns in that, say 4 columns are present, so something like this you offer. So 1, 2, 3, 4. So Kb is equal to K1 plus K2 plus K3 plus K4. Now how do we get K1? K1 is nothing but 12 EI by h cube of this column, next is this column, next is this column, next is, that's how we get total stiffness of Kb. Similarly Kd. So we are giving displacement of ux in this direction, right side direction, then the resisting force will be Kb and Kd together. So if this is unit displacement, then Kb plus Kd is a force. So that Kxx force is nothing but Kb and Kd. Then what is force along say y direction? Because there is no force available in that direction, no resistance in that direction, 0. Then theta. So theta direction rotation is in this. So Kx theta. So Kx x direction, Kx y direction, Kx theta direction. So that is, you can see this one clockwise. So if we take moments of the forces at this location, Kb into B by 2. So this is B by 2 lever arm, Kb into B by 2 minus anti-clockwise Kd into B by 2. This is Kx theta. So this is one column of stiffness matrix. Similarly, we write second column. In second column, for writing second column, what we do is kx is equal to 0, ky is equal to 1 and ux is equal to 0, uy is equal to 1 and u theta is equal to 0. So we are giving 1 unit displacement along y direction. So ka into uy, kc into uy. So if uy is 1, then what we get is, so along x axis there is no force, so that is why 0. Along y axis two forces are there, so ka and kc, so we add that. And then along theta axis, again along this direction we need to, so kc into a by 2, this is a, so half of a is, this is a by 2. So kc into a by 2 minus, this is anti-clockwise direction, ka into a by 2, this is ky theta. So this is second column of stiffness matrix. Now when it comes to third column of stiffness matrix, so how do we generate that? Ux is equal to 0, uy is equal to 0 and u theta is equal to 1. 1 unit rotation we are giving. So if we give 1 unit rotation, what happens is, so this point comes up to this, so 1 unit rotation, theta is 1 unit. So then how do we get this value? So angle is equal to arc by radius. So radius is say a by 2. So theta is equal to arc by radius. So this is a delta by a by 2. So if theta is 1, implies delta is equal to a by 2. So this value is a by 2. So that means what? Ka into a by 2 is the force in this direction. Similarly, kc into a by 2 is force in this direction. Here, so since it is rotating in anti-clockwise direction, all the forces will, resistance will come in clockwise. So that means upward, right side, downward, left side. So this kb into b by 2. So because lever arm is b by 2 here, so b by 2. Again kc into a by 2, kb into b by 2. So these are the forces in that direction, corresponding directions. Now equilibrium along x, y and theta direction, force equilibrium. So we can get k theta x direction forces are kb into b by 2 minus kd into b by 2. Then y direction, k theta into y direction, kc into a by 2, ka into a by 2. Then k theta direction means what? So the force we need to generate moment at this point. So that is because of the rotation. So ka into a by 2 into again a by 2 from here to here. So like that, kb into b by 2 again b by 2, kc into a by 2 again a by 2, kd into b by 2 into b by 2. So we have k theta we wrote here. So then final stiffness matrix is this. Okay, all terms placed here, that is giving final stiffness matrix. So now in this one, what is happening is, so mass matrix, when mass is moving in say x direction, entire mass is having the same acceleration value. So that is why whole mass is participating. In y direction, so in this demonstration we will discuss about center of mass. So what is center of mass? So in a building, when mass is distributed uniformly, center of mass will lie at the intersection of diagonals. So if I move this building, it will move straight because I am applying force at the center of mass. But if I am adding some mass, additional mass at some location here, okay, then again I start moving this one, this building is twisting. So why this building is twisting? Why not the earlier case? In earlier case, mass is distributed uniformly. In this case, additional mass is present here, that is why building is twisting. So in 3D analysis of buildings, we need to find out first center of mass. So when center of mass is located at the center and center of stiffness is also located at the center, then we will not have off diagonal terms in stiffness matrix. But if center of mass is slightly shifted and then center of stiffness is say at some other place, then even if we start translating our motion in translational direction, then building will twist. So we will have off diagonal terms in the stiffness matrix. So So, we need to, as far as possible, we need to maintain center of mass and center of stiffness in a close proximity. So, let us solve one problem where one directional symmetry is there. So, Ka is equal to K, Kb is equal to 2K, Kc is equal to K, Kd is equal to 3K. So, in that, so it is something like this problem is given in this form. Ka, Kb, Kc, Kd. You can see along this direction, y direction, there is symmetry, along x direction there is no symmetry. Why there is no symmetry? Because here 2K and 3K, so no symmetry is there, because center of stiffness will shift along this direction. But when it comes to y axis, so K and K both are there, so symmetrical about y axis, unsymmetry about x axis. So, if we formulate Kxs, Kx y theta in the using this previous formulation, so we get this stiffness matrix. So, as you can see, off diagonal terms are present. So, that means what? When off diagonal terms are present, if we move in one direction, so of unsymmetry, it will rotate in the other direction also, it will translate in the other direction also. So, but if we give motion along y direction, it will not translate, but if we give motion along x direction, it will translate along x as well as y. But if we give motion along y direction, it will translate only along y direction. So, that is what is a directional symmetry. So, now we have M mass matrix, acceleration vector, stiffness matrix, displacement vector, and earthquake ground motion. So, in this one, so the symmetry is if I give only x direction acceleration, it will displace in x direction as well as y direction and as well as theta direction. But if I give y direction only, not x direction, this is 0 and this is 0, it oscillates in y direction only. So, that is what is given, that is what we can understand from the dynamic equilibrium equation. So, now to come out of this one, we need to do decoupling of these equations. So, how do we do decoupling? So, decoupling means again we find the mode shapes and pre-multiply and post-multiply, then we solve the problem and then back calculate it. Now, if symmetry is there along both axes, so that means what? All stiffnesses are same. So, when all stiffnesses are same, so it is something like this: Ka, Kb, Kc and Kd. So, all values are K. There is symmetry in both the directions. So, what we get is, so 5K, 2K, Ka square. So, this is stiffness matrix, mass matrix is there. So, as you can see, the equation will be mu double dot x 5K into ux. So, each equation is independent, you can see this one. So, you can solve this equation to get ux, you can solve this equation to get uy, you can solve this equation to get u theta. So, this cannot happen in the earlier case where one dimensional unsymmetry was there. In this class, what we have studied? So, we have studied how to formulate the stiffness matrix for 3 degree of freedom system. So, that is real 3-dimensional buildings, and then one directional unsymmetry will affect the motion of the other direction. So, that we have studied, and how to decouple this one. Decoupling can be done by using again the same principles as in the case of multi-degree of freedom systems, that is u is equal to pi multiplied by q. As far as possible, symmetry should be ensured in buildings for not to have torsion while earthquake ground motion is applied onto the buildings. So, we will solve an example problem and understand this one, and also we will solve an example problem of how to find out center of mass and center of stiffness.